All right, for a long time now, we've gotten really good at telling robots where to go. But what if we could teach them how to feel? I mean, really feel. That's the big leap, right? Moving past just go here, go there, into the world of dynamics. Today, we're going to dive into how we control the forces a robot puts out, basically giving it a sense of touch.
So that's the big question, isn't it? How do we actually make that happen? Well, it means we're leaving the world of pure kinematics, just positions and speeds, and jumping headfirst into dynamics. And this is huge. It's the key that unlocks all those tricky, delicate tasks. Think about assembling something tiny, or polishing a surface, or even just putting a glass down on a table without shattering it. It's the difference between a clumsy machine and one that interacts with skill.
Okay, so here's the game plan for today. We're going to start with the basics, the language of forces. Then we'll get a quick win by just fighting gravity. After that, things get cool. We'll program a virtual spring, figure out how to give the robot a delicate touch, share some hard-won lessons from the lab, and then wrap it all up to see the big picture.
All right, first things first, let's talk the language of forces. Look, if you want to control force, you've got to understand the physics behind it. And lucky for us, it all comes down to one incredibly powerful foundational equation.
Okay, here it is. This is the equation of motion for pretty much any robot you can think of. It looks a little intimidating, but let's just walk through it. Q is just the robot's pose, its joint angles. Then you've got MQ, the mass matrix. Just think of that as the robot's inertia, how much it resists being pushed around. C is a bit more complicated. It's all the weird interaction forces that pop up when things are moving and spinning. GQ, that's the easy one. It's just gravity pulling on all the joints. And finally, the one we really care about, tau. These are the torques from the motors. This is the thing we can actually control. It's our lever.
But wait a second. How do we even know this math is right? I mean, is our model actually accurate? Well, we have to check our work. We do what's called cross-validation. We take a pure math library, in this case one called Pinocchio, and we pit it against a super detailed physics simulator, MuJoCo, and just look at these numbers. When we compare their calculations for gravity and the mass matrix, the error is, it's tiny. We're talking millions. So what does that tell us? It tells us our foundation, our understanding of the physics, is absolutely rock solid. Okay, so we've got a model we can trust. Now it's time for our first win. We're going to start with something that sounds simple, but is actually super fundamental for dynamics. Just having the robot hold its arm perfectly still against gravity.
And you know what? The solution is just beautiful. It's so elegant. All we have to do to cancel out gravity is command our motor torques, our tau, to be exactly the same as the gravity vector, g of q. That's it. Our model figures out how much gravity is pulling down, and we just tell the motors to push up with the exact same force.
So why does this work so well? Let's go back to that big equation. When we set our command, tau, equal to g of q, they just cancel each other out. Poof, the gravity term is gone. Suddenly, the math says the robot should behave as if it's weightless, like it's floating in space. And because every real joint has a little bit of friction, we call it damping, any tiny wobbles or movements just die out almost instantly. The robot just holds its pose. Perfectly.
And wow, do the results speak for themselves. The maximum error, the most it drifts, is less than 9/millionths of a radian. That's almost nothing. It's so incredibly stable. The arm is just locked in, totally effortless.
Okay, but what if we mess with it? What happens if we give the robot a good bump, a perturbation, as we call it? It settles down almost instantly. The final speed is basically zero. The controller just actively fights back against that push and goes right back to holding still. This right here is our first big, powerful example of dynamics in action.
So, holding still is cool. That's a great start. But let's build on that. What if we don't want it to be perfectly rigid? What if we want it to be a little compliant? A bit springy? What if we could literally program it to act like a virtual spring?
This equation right here is how we do it. It's called impedance control. Now, I know it looks a little scary, but the core idea is actually pretty simple. We're telling the robot's hand how to behave like a spring in the real world in normal XYZ space. That J thing, the Jacobian, that's just the math magic that translates that springiness we want at the hand back into the torques the motors need to create. And hey, look at the end there. See that plus g of q? We're building on what we already did. We always cancel out gravity first, and then we add this new springy behavior right on top.
And the best part is we can tune this virtual spring however we want. That Kp term, think of it as our stiffness knob. If we set Kp low, the robot is soft, it's compliant. a 40 Newton push, and it gives way by more than 10 centimeters. But if we crank that KP knob way up, it gets super stiff. That same push only moves it 17 millimeters. We can literally program how it feels from one moment to the next.
Okay, so we can hold a pose, we can act like a spring. Now, for the main event, let's combine these skills to get that truly delicate touch. We're talking about tasks like writing on a whiteboard or tracing a line on a table, things that need you to control your position and your force at the exact same time.
Now here's the trick. You can't control position and force in the same direction. Think about it. You can't push down on a table with exactly 5 newtons and be at a height of exactly 0. It's one or the other. So the big brain move here, with what's called hybrid control, is to split up the job. When you're tracing on a table, you use a position controller in X and Y to move along the surface. But in the Z direction, you switch gears completely and use a force controller to maintain a constant, gentle pressure down into the surface. You decouple the problem.
And the performance is just amazing. We told it to push down with 5 newtons of force. And look at this. It stayed within a tight little window around that target 99.96% of the time. And it did that while it was moving, keeping its position error under 2 millimeters. That's what we're talking about. Precise, controlled, delicate contact.
Okay, but let's be real for a second. Getting these kinds of results isn't as easy as just typing in the equations. So let's do a little rapid-fire round of some really important lessons we learned when our perfect theory smashed into messy reality.
Lesson 1. Your model has to be right. Seriously, we were pulling our hair out at first because our math model and our simulator just would not agree. And you know what the problem was? We forgot to properly include the mass and the inertia of the gripper on the end of the arm. So the takeaway is huge. When you're doing dynamics, the thing you're carrying isn't just some optional detail. It's a critical part of the physics.
Lesson 2. Reality is way more complicated than you think. Our first plan assumed the robot would only ever touch the table with the very, very tip of its tool. But in practice, sometimes the wrist bumps into it or another part of the gripper makes contact, and our whole force control plan just fell apart until we updated the logic to account for contact happening anywhere on the end of the arm.
And lesson 3. This one's a big one for stability. Our first tries at force control were a disaster. The robot would just chatter and vibrate against the table. It was awful. Just telling it push with 5 newtons wasn't enough. The secret sauce for getting that smooth, stable contact turned out to be 2 things. First, you have to smooth out the noisy data coming from the force sensor, and second, you have to actively kill any speed going into the table. You got to damp it out.
Okay, let's take a step back and look at the big picture. Let's put this whole journey into perspective, from that first line of code all the way to making controlled contact.
What a road, right? We literally went from a single pure math equation all the way to an advanced robot that can trace a line. We started with that fundamental equation of motion. We used that to beat gravity and get a rock-solid hold. Then we built on top of that to create a virtual spring. And finally, we pulled it all together to give the robot a truly delicate, controlled sense of touch. And really, that brings us to the most exciting part. We've gone way beyond just telling a robot where to go. We've actually given it a sense of touch, an ability to feel and interact with the world with real precision. So I want to leave you with this one big question. Now that our robots can actually feel, what amazing, complex, delicate new things can they finally master?